So, welcome to the last unit of the module on addressing mode, instruction set and instruction execution flow. So, throughout this module in the last 7 units basically we have covered mainly different type of instructions, their format, their operand types, what are the addressing modes, and finally in the last unit we covered a very special type of instructions which are actually called conditional instructions, that is which are not a very sequential flow, but depending on some conditions of variables like 0 flag or some other conditions like equality, parity, etc., we can jump to a required memory location to execute the instruction from that part, or if the condition is true we can just go ahead to the next instruction. And then we had seen that flags play a very important role in control instructions. Flags are some of the register bits which are set or reset depending on the conditions of some mathematical or logical expression. Like for example, if you add 2 numbers, then if the answer is 0, then the 0th flag is set. Then you can use a conditional instruction called jump on 0 using that flag bit. Now, today in the last unit, that is we are going to use such conditional instructions in a very practical application which is called the procedure return and call. So, if all of us we have written some C or C++ high level language codes, and we know that functions or procedures are a very important part and parcel of all programming language, because you can modularize your code. But what happens is that whenever you are running a main code, from there you have to call to a subroutine or a function, and then from that function you can call another function and it can go on. But what are the issues there? The first very simple issue is that you have to know at which location I am going to jump. So, there should be a jump instruction. So, it can be conditional or it can be unconditional. Conditional means if it is based on some condition, if you want to call the instruction, then it will be a conditional jump procedure call, but in most general cases we generally just call the function from certain part of the code. In that case it will be just a function call which would be an unconditional jump. But then whenever you are leaving your main program, then obviously you want, after executing the procedure, you have to come back to the main program and start executing from that point. So, you have to save the context of the program when you are jumping to a subroutine. So, all those issues we will be covering today in this unit. So, this is the last unit of the module which is on procedure, call and return. So, as a pedagogical format, so what we are going to study, what is the unit summary. So, basically as we have told that procedure is a self-contained computer program which is a part of a larger program. So, whenever a procedure is called, basically it invokes a jump to the memory location where the first instruction of the procedure is placed. So, it is some form of a unconditional jump, but sometimes we can also have a procedure whose call may be depending on some condition. In that case you have to call the procedure based on some conditional instruction, but in a very general sense we generally have a unconditional jump or unconditional call to the procedure. Then again, as we are jumping to a new procedure, so we will be reusing all the temporary registers, the accumulators, the program counter. Program counter actually gets changed from the current programming location to the location of the first instruction of the procedure. But again, when you want to return back, you have to again come back to the point where I have left the main program. You have to also regain the values of the registers where there are some temporary variables which I was working on, and so forth. So, in other words, the whole context of the program has to be saved in a stack. So, very important components of the stack are basically, we call it as the program status word, which will have all the values of the flags, which will have the value of the program counter, or in other words the context of the current program has to be stored in a stack when you are calling a procedure. And when we are returning from the procedure, all the values of the context like the value of the program counter, the value of the registers, etc., are fed back to the corresponding registers and the program counter, so that you gain the real context from where I have left in the main program and you can start re-executing. And if they are nested procedure, as we will see in an example, so procedure A will call procedure B will call procedure C, and at every call the context of the calling procedure will be stored in a stack, and when you are returning, unwinding the procedure calls, you are going to get back one context after the other from this stack that you are going to see. So, these are two very important concepts, jump, and before you jump you store everything like the return address, the program status word, the value of the registers, etc., or the temporary variables or the temporary context of the procedure or the main function which calls another procedure are saved in a stack. And when you have to return back after completing the called procedure, then you have to regain back the values and you again start executing. So, these are the very two basic concepts which we are going to deal in detail today. And then what is the unit objectives? in there are three basic objectives, that is knowledge in which you will be able to describe the concept of modular programming which uses a procedure of a function. Then you will be able to comprehend and discuss the basic requirements of CPU organization for a call function, that what are the registers required, what is the stack required, etc. And as a synthesis objective, you will be able to explain the design issues of return and call instructions, that how can you design the call instructions, how can you design the return instructions, what are the issues, which are the registers involved, what are the stack involved, etc. what are the hardware of the CPU involved to design call and return instructions. So, these are the basic objectives which you are going to fulfill after running this unit. So, as we are all very much familiar with C programming, so we are going to take a very simple C program with a subroutine and see how it reflects in a assembly language. So, it is int a equal to 5, b is equal to square of r. So, this is a function in which you are making a square, that in this case actually this is b equal to a square. So, what is the function? So, you are calling this the function. So, you are passing the value of a, then in square, then square val equal to val into val is passed over here. So, a is passed is the function a. So, we are going to get the value of a square, because the variable val has the value of a which was passed as a parameter, and then you are returning square val, that is the square val is nothing but value of this square of val, and that is nothing but in this case a square, and that is going to be returned to b, and you are going to get b equal to a square. Very, very simple C procedure. Now, if you look at it, how the subroutine would look like. So, first we are taking a value of the memory location a into register 1, then it is a, so now register 1 has the value of a. Now, what you are doing, you are making a jump unconditional to a procedure whose name is square. So, again this square here is a subroutine, but as we were discussing yesterday, as a part and parcel of every jump instruction there is something called label. Label means nothing, it is a name given to an instruction, when the code is loaded into a memory, it is going to be replaced with the exact memory location of the instruction which you are going to call. So, in this case square root is the label here, and it is nothing but it is the pointing to this instruction, or it is the name of the instruction. So, jump is an unconditional jump subroutine, it will just go over here. Square root means the name of the instruction, or it corresponds to the memory location of the instruction where this instruction is stored. So, it is mul r1 into r1. So, already you have the value of a into r1. So, you are going to give the value of r1. So, it is nothing but it will be r1 square. R1 into R1, it will be stored into R1. Then R1 is going to have the value of a, basically a square. Now, you are going to move the value of R1 to R2. So, that is now R2 has the value of a square, and then you are saying that I am going to return. So, when I am executing the return statement, what happens? So, when I am calling this one, you have to store all the value of the temporary variables, temporary registers, as well as most importantly, you have to store the value of the memory location for the jump instruction. Because when I am going to return from here, I have to go back here, and then I will do, what I will do is that I have come back to from the point which I have left, increment the value of PC, and you come over here. In other words, whenever you are jumping from main procedure program to procedure, you save the value of the program counter at this page, at this part. Then now this is maybe the program counter say 5, so 5 is stored in a stack. Here program counter may become 20, because 20 may be, are we assuming that the memory location starting address of the subroutine. So, 20, 21, 22 it will go on, and whenever it is going for the return instruction, the value of 5 will be popped from the stack, so that you can know that now the program counter value is 5, which is the place which I had left. Then it will become 6, and you are going to execute the instruction in which is called move R2 to B. So, in this case the value of R2 will be moved over here, and if you look at the program carefully, R2 is nothing but it is basically R1 square, that is nothing but A square. So, A square will be transferred to the value A, this instruction will be transferring the value of A square to B, which is actually the requirement of the program. So, in fact, this is some background information which I have given you, which is required to understand that how a subroutine is converted into an assembly language code. Then now we are going to see basically what are the components required, or what is the hardware required in the CPU for a procedure call. So, as I told you, when a subroutine is executed, the main program is stalled and the subroutine is executed. When the subroutine is completed, it returns to the main program. So, there is some, so program counter will play a very important role over here, and the value of program counter when calling a subroutine has to be stored. If the subroutine calls another subroutine in a nested manner, then actually the storage of the program status word, the storage of the registers, the storage of the PC will be in a recursive manner as of a recursive, simple recursive function call in a stack. So, when A calls B, B calls C, C calls D. So, you put all the context in a register, in a stack, and whenever you are finishing one subroutine after another, you are popping up the corresponding program status word, registers, PC in a return procedure return manner. And so, basically that is what is being said. When we move from one subroutine to another, you are saving program counter, program status word, register variables, etc. And when you are popping back, so it is when you are returning from one procedure to another in a nested manner, or returning back. So, one after another the context will be fetched from the stack. So, in fact, you require basically a program counter, memory, everything is required, and in addition you require a stack which is holding all the components or the context of the programs or the subroutines when a call is made from one subroutine to another. A stack is a very important component of a procedure call, if you look at the hardware terms. So, as I told you, so program counter, program status word and register variables are very important components which are stored in a stack which defines the current context of a code. In fact, the flag registers was also saved basically, because when you are running a current set of instructions, the flags are set or reset, which are also used for some conditional statement. When you go to a subroutine, the same program flag registers will be used, but now it will be used in the context of that procedure. So, in that case you have to again save back the value of the flag register, and you have to again, when you come back from the procedure to the main code, again you have to regain them, because they are shared resources. This program status word, program counter, variables, registers, they are actually shared components of the CPU among functions and main function and several procedures. So, you have to save the value if you are moving from one procedure to another. Now, where is the stack implemented? So, the group of main memory is used to implement the stack, that is very important. You can save a particular part of the main memory to implement the stack, and there is a special stack pointer which will actually locate that where the top element of the stack is. So, basically in fact a part of the main memory is reserved for this stack. So, something like this is a pictorial representation. So, it says that subroutine B is nested in subroutine A. So, in fact what it says, there is a main program, then it will call program A and it will call program B. So, in this case if you see, when the main program is calling procedure A, then what happens, the variables of main will be saved, program status of word of main will be saved, the PC of main will be saved, and other temporary flag registers of the main memory will be saved, and so forth. Then actually from here you are going to go to the procedure A. From procedure A, procedure B will be called. So, whenever you are going from procedure A to procedure B, of course you have to store the same elements as of the main program when you are calling procedure A from procedure B. So, you are saving the value of variables of A, program status word of A, registers of A, program counter of A, flags of A in this stack. Then you are calling B. So, now from B you may go to C and so forth, and then afterwards what happens, when you return from that, you regain the value of PC, you regain the value of program status word, you regain the value of variables and complete the execution of B. Once it is done, you will return from B to A. Similarly, now again you get back the value of PC of A where you have left from while calling A to B, then you again restart from the point where you have left in B. So, before that you regain the values of variables of A, program status of A, etc., and the PC will be loaded at a point from where you have left A to execute B. After completing execution of A, you do the same thing for the main program, and finally the whole code stops the execution. So, what I was telling you in a nested manner in a stack is represented in a nice pictorial manner in this slide. So, important components of a procedure call: everything, program counter, instruction decoder, arithmetic and logic units, and very important is a stack pointer and a stack. In fact, the main memory is actually the part of implementing the stack, and stack pointer is a very important. It can be actually nothing but another variable or a register of the stack pointer which will actually contain the address of the main memory which is the top of the stack. So, the whole main memory actually is there, you are allocating a part of the main memory for stack. So, maybe you can say that this is my stack pointer. So, there will be a special register which will hold the value of the top of the stack, because after adding some more elements, it will come over here. So, every time you have to recollect which is the top of the stack. So, whenever you want to pop some element from the stack, so you will read the variable or the register which is having the stack pointer, you will load the value of the stack pointer to the memory address register, and then you can easily start popping up the values. Obviously, as I told you, as the stack is implemented in the main memory, so main memory is a very important component of the function procedure call. Of course, memory address register will be required because we are going to pop up the elements. Where is the value of the memory address register? In the case of stack, it is in the stack register. So, stack pointer. So, stack pointer is nothing, but it points to the top element of the stack. So, when you want to fetch the element from the top element of the stack, what you have to do? You have to get the value of stack pointer to memory address register, and then you can fetch the value in the memory data register. But importantly, so I need a variable or a register to implement the stack pointer. It is nothing but the address of the main memory which is stored in a register, and it corresponds to the address of the main memory where the last element which was inserted in the stack is present. Then of course, system bus, registers, everything is involved in the implementation of a procedure call. So, this is nothing but your whole how a CPU looks like. What is the CPU bus? So, therefore, you can see there is an instruction register, there is decoder, there is instruction register, there is all the user registers, program counter, memory address register, memory data register, that is memory buffer register, arithmetic logic unit, you can call it as the accumulator. So, all the components which we have talked till now are all available. Importantly, I want to point out is the stack pointer. So, stack pointer here is nothing but a special register which is going to hold the address of the main memory where the last element that was pushed in the stack is present. So, whenever you want to pop an element from the stack, what you have to do? You have to just SP will put the value in the memory address register. So, it will say that I have to pop one element. So, SP will be given to the memory address register, that value from the memory will be fetched and it will be fed back to the memory data register, and from the memory data register it can go to the instruction register, it will go to the instruction decoding register, instruction will be decoded and the code will be executed. So, this is overall the basic CPU components which are involved in a procedure call. All the components are quite similar to all other functions and all other instructions we have discussed till now, but stack pointer is a register which plays a very special role over here. Now, we have talked enough theory, and this actually in a nutshell what I have told you completes the theory of a procedure call. It has basically only 3 very simple steps. You call a procedure, before calling a procedure, save everything in the stack, call the procedure, jump to that instruction where the first instruction of the procedure is there, jump to that memory location. After completing the procedure, return back to the main program from where the procedure is called, and at the same time before jumping back to the main place where you have started from where the procedure is called, you have to regain back the values of the program status word, the program counter, variables which you have saved before going to this one. So, save, that call means save the context, call the procedure, that is go to the procedure and complete the procedure, return back to the main part of the program from where the procedure was called, and before returning back you have to regain what you have saved. So, it is a very simple way of implementing a procedure. Now, it is better that this was all from a theoretical context. Now, we are going to look at in a very simple example. So, we have a processor whose memory address range is 000 to FFF. So, it is a address bus will be 12 bits. The memory contains, and as I told you, so this is your main memory. So, it will have 000 to say FFF, and a part of this is reserved for the stack. So, what is reserved for the stack? If you see FF0 to FFF, maybe some from here. So, this part of the program memory is allocated for a stack, where your stack will be saved, and it is assumed that the stack goes downwards. That means, you will be going downwards as a stack implementation. Okay? And the main program is located from 1100 to 2CF, procedure A 300 to 3B0, procedure B is located from memory location 3C1 to 3EF. So, basically it has 3 programs. One is the main program whose location is 110 to 2CF, procedure A is loaded in 300 to 3B0, and procedure B is loaded at 3C1 to 3EF. And memory location from the main memory at location 1CD, which is in between this, we will call procedure A, and memory location call A instruction is at CD. So, in the main memory program at 1 CD memory location, call A instruction is present, that is when the main program will be at instruction which is located in memory location 1 CD, it will be calling procedure A. Similarly, while I am executing procedure A, then this instruction which is in place of 37A as a part of procedure A, it will call procedure B. That is, when I am executing the main program, it will call procedure A at memory location 1 CD. That is, the call A instruction is located in memory location 1 CD. When I am executing procedure A at memory location 37A, the instruction call B is there, and after executing call procedure B, you will return back to A, and then again you return back to the main program. So, we look at details what is going to happen. The stack pointer at present is F20, that is the top of the stack, it is assumed. So, let us assume that the stack pointer is this at some point of time, this is your stack, this is the part of the main memory which is allocated for the stack pointer value is there. We are having 4 general purpose registers which will hold the values. It is your scratch pad kind of a thing, which are the general purpose registers which are given to you to basically for user programming, for use in user programming. Stack pointer, program counter, all are also present as a general CPU architecture. So, they are all available over here. So, now we will see how the stack is implemented or how the stack is modified when such a code is executed using jump instructions in a nested procedure, which example is given below. So, if you look at the pictorial representation, we start main program at 110, end at 2CF, okay, and then if you look at it, 1 CD is the instruction of the main program which is calling function A, subroutine A is starting at 300, ending at 3B0, at 37A location it is calling procedure B who starts at 3C1 and which ends at 3EF, and after ending of the procedure again you go back. So, this is the pictorial representation of the nested call which you are going to see. Okay. And this is the example of the stack. So, this part of the memory has been allocated for the stack. So, the memory is written in a reverse manner, basically FFF to FF0. In fact, if you go dot dot dot, this will be 0 0 0. So, they have not written the memory in this fashion like 0 0 0 to FFF. They are just illustrated in a reverse manner. That is not a problem. Just we have to think about that this is the last location and the 0th location is down the line. Okay. So, and this part of the memory is allocated for your stack implementation. Sorry, this part of the whole part is allocated for stack implementation, and at present the stack pointer is here. There may be some other elements over here which we are not bothered for the time being, but our stack pointer is at this point, and so we have to think about this stack which actually starts from here in this range. Okay. Sorry. Okay. So, now we have built our context, and now let us go ahead with the implementation. So, our stack was at 20. If you remember, our stack was pointing over here. Now, main program is calling the procedure A. So, now we are at 1 CD. So, at this point the main program is calling subroutine A which is located at location 300. So, basically our stack pointer was here, then first PC is equal to 1 CD, location from which the call to procedure A is intimated. So, you see 1 CD is the location from which the call is there, call has occurred. So, what you have to do? First you have to store the value of 1 CD in this stack, this one, because when I will be returning back to this point. When I will be returning from subroutine A to main program, after of course going for subroutine B, so this is subroutine B, this is actually subroutine B, there is a mistake over here, this is nothing but subroutine B. So, when after executing subroutine B, you are going to execute subroutine A, and then after that you are going to come to the main program. So, I have to remember the value of 1 CD, because after that I have to start executing from 1 CE, that is the next instruction. So, I have to save the value of 1 CD. So, the value of 1 CD is saved over here. Next, we are going to save the program status word of the main memory, that is a lot of context, flag registers etc. will be saved, and then I will also save the value of the 4 registers. This is the context which is saved of the main program in stack before I go to memory location number 300 where the program procedure A starts. So, 1, 2, 3, 4, 5, 6, 7. So, 7 values have been stored, and now your stack pointer will be placed over here, because as I told you, stack pointer points to the memory location, in this case F14, where the last element was pushed into the stack for the current set of codes being executed. So, this actually slide very clearly shows that when I am calling procedure A from main program, the main location for when the procedure call is initiated is 1 CD. So, that is the program counter at that point, it is first saved, then the program status word of main memory is main program is saved, which is the flag registers and several other values of the intermediate variables are stored. Then the user registers like R1, R2, R3, R4, R0, R1, R2 and R3 are saved, and then you go to jump to memory location 300 where the procedure A starts. But now the 7 elements have been saved. So, your stack pointer will now point to F14. So, now whenever from A to you will be calling procedure B, so it will start filling up from here. So, now look at here. So, here call B. Okay. So, after this if you remember, this was the part for main program. Now, from here I am going to call program B. That is procedure A is going to call procedure B. So, while jumping to procedure B, you have to do the same thing, you have to save the value of 37A. So, 37A is nothing but the part of procedure A or the location of procedure A from where the procedure B is called. So, you have to store 37A because when you are be completing procedure B, you have to return to the point in procedure A from where procedure B was called and you have to complete A. So, you have to remember basically 37A from where procedure A called procedure B, because after completing procedure B you have to return to memory location 37A and then you will start executing the next instruction, that is 37B. Of course, you have to again store all the values of the context of A, user registers of procedure B, because these user registers when were executing the main program were saving some values which were local to the main program. When I am going to procedure B, the same set of registers will be shared between main program and procedure A, but then procedure A will again save some values which are required to be saved or called or this one which are local to A. For example, I may use in the main program to store the value of C plus D in R0. When I am calling procedure A, then I can use the same register R0 to compute some other stuff which may be F plus G. So, the resources are same, these registers are same for procedure A, main program and procedure B. So, therefore, the local values involved in the registers has to be saved when you are leaving that procedure and calling some other procedure. Then again the program stack will again get incremented by C. So, it will come down by, it has already saved another 7 values. So, now the stack pointer will be pointing over 7 and then it will move to 3C1 which is nothing but the place where this one is called. So, I am going to 3C1. So, this is nothing but the instruction location where procedure B starts, and then procedure B is done. So, then procedure B will start executing, and when procedure B will be completed, it has to regain back. So, after procedure B is completed, what you have to do? You have to start executing procedure A from the point which we have left. So, if you see, if you remember, 37A is the point where I called B from A. So, you have to, when I am completing, so my stack pointer is here. So, when I am completing procedure B, see that is the 3EF which is the last location of procedure B, then it is start unwinding. So, what will happen? Then procedure B is finished, now it has to return. So, now what will happen? The stack will try to find out that where I have to return. So, it is nothing but procedure A where you have to return. So, how the whole computer will know that what I have to do. So, it does not understand or does not remember in a very explicit sense that A called B, B called C, not in that way. B has ended, that is the last instruction of procedure B has completed. Now, it is a return instruction. So, whenever return instruction is executed, it will first look at the stack pointer. So, stack pointer will start refilling the values in the respective registers. So, procedure B has completed, return instruction is executed. Now, this part is invoked. What it is doing? Stack pointer is 7. So, whatever is in the stack, first stack pointer will be fed to register 3, 2, 1, 0, PSW of A, PSW other parts will be loaded in the corresponding registers and main and the registers and the flag registers, etc. So, up to this, the whole context of A will be loaded into the respective registers. That will be automatically done when B will be doing a return instruction. B is executing a return instruction means the stack pointer starts incrementing one by one, that is they are popping out all the elements and feeding in the respective registers. Then the program counter will be loaded at 37A. That is, now it will return back to A. Then at procedure A, 37A is the location where I left A to go to B. Then program counter will be incremented by 1. So, it will be 37B and procedure B will be executed. Basically, this is what is the situation. So, in this case the whole stack which was corresponding to A is gone. It has been fed to the corresponding registers and the program status part of A. The A code has been started to execute from memory location 37B and A will complete. So, when procedure A is running, so this is the part of this stack which is in context. The stack pointer is over here and these are the elements which corresponds to the main program. But at present we do not require the context of the main program right now, because now procedure A is running. Once procedure A will be completed, then what is going to happen? The same thing which I discussed for the from B to A, the same thing will repeat for the case of A to main program. So, the stack pointer was at 14. So, if you remember, 33B0 is the last location in which the procedure A was called from main location. So, you have to so from 3B0 is the last location of procedure A and when return is called. So, last location of program counter is 3B0 in procedure A when return is called. That means, at 3B0 A has stopped. Then whenever, as I told you, whenever a return instruction is called, these R0, R1, R2, R3 will be now fed to the respective registers. So, what will happen? So, the R0, R1, R2, R4 till now we are having the values corresponding to procedure A. Now, they will be eliminated and the values of registers corresponding to the main program will be loaded into the register. Similar thing will happen for the program status word. Now, what is going to happen? Now, one CD will be loaded in the program counter. That is very important, because one CD is, if you remember, one CD is the place where the main program called the procedure A. So, now this will be incremented, it will be 1CE and the main program will start executing from 1CE, and finally the stack pointer also before starting the execution in the main program which called A, the stack pointer will be pointing over here, the whole stack will be empty, the main program will be executed and finally the whole code will stop. So, this is what will be your stack, because after I am loading all the context to main program, then there is no other code which remains to be executed in the nesting. So, procedure main program A, B, from B to A to main program, and the whole stack is cleaned. So, this is a very simple way in how a procedure is basically implemented. So, now we are going to see a slide, because we are this is the last lecture of this module. So, in the next module, which will be going into more integrated way of understanding how basically the codes are executed in terms of micro instructions. So, what we are going to see now, so when you are going to say pop, when you are going to say push, when you are going to say jump, when you are going to say return, how actually what are the set of assembly language instructions that are executed, like push, pop, actually involves some kind of micro instructions. Like when I say push, so what is going to happen? Push means first you have to take the value of the stack pointer, because it is pointing to the main memory. So, that value has to be loaded to the memory address register, then the value from the memory buffer register will be loaded to the memory and then it will be again decremented. So, because when I say pop, so what is going to happen? Again the stack pointer value has to be put to the register memory address, because only a part of the main memory is given for the stack implementation. So, again when here the pop means the stack pointer value will be loaded to the address register, then the address register will point to the memory address which is having the corresponding value for that stack which I want to pop. So, that value of the memory will be going to the memory data register and that will go to the instruction register and so forth. So, in fact, push, pop, call and return. So, if you want to call, then what you have to do? Before you have to call, you have to push so many instructions into the main into the stack, and then you have to jump unconditional to a place. So, all these push, pop, call and return will have some kind of a micro instructions. So, now we will see basically or micro operations. So, how basically call, return, push and pop are implemented in a micro level. So, when I say push, it is very simple. So, the stack pointer will be loaded to the memory address register, and then so now the memory address register is having the value of the point in the stack which I want to push a value. So, the register Ri will be written to the memory buffer register and finally the memory will be written. It is something like this. So, this is your stack pointer. So, stack pointer basically will be sorry. So, this is your memory address register will be pointing to the memory, that is your stack. So, this one will be fed by the stack pointer. So, stack pointer is a register, it will be written to the memory address register, then it will be pointing over here, then the memory the data will be going to the memory buffer register, and the memory buffer register this will be stack pointer, the memory is a push. So, it will be the other way around. So, the memory buffer register will be written from the RI, because I want to store the value of memory register RI to a memory location, and in which memory location I want to put, that is the stack pointer. So, the value of stack pointer will be given to the memory register, memory address register. Memory address register is pointing to the point in the stack where I want to push the value, but who writes to the memory? If you remember, the memory buffer register is written to the memory as well as read to the memory. So, in this case it is a write operation, because we are pushing it. So, the write signal will be made high in the memory, the register RI will be written to the memory buffer register, already the address register is pointing to the top of the stack, and then the value of the memory buffer register will be written over here. In case of POP, it is just the reverse, same thing. So, this is your memory address register, you are writing the value of the memory register from the stack pointer. So, you are pointing to the exact location of the stack from you want to pop the value, then you make a read. So, that it will come to nothing but the memory buffer register. So, stack pointer will give the address to the memory address register, memory address register will point to the address location in the stack from where you want to read, you make a read signal, and then your memory buffer register will be getting the value, and memory buffer register will be writing to the memory location from to the register RI. So, RI is going to gain back the value which we want. So, it is very simple of a push and pop operation. Now, call. So, call is slightly complex, means before you call there are so many stuff that has to be done. So, say I want to do a call location, call. So, what I will have to do? So, call is nothing but a jump instruction. So, before doing it, we have to push all the elements to the stack, like the program status word, where you have to return the context, and then you go for a unconditional jump. So, what you have to do? So, this is your stack. So, whenever you want to do any instruction like return, call, push and pop, you have to first load the value of the program, you have to first load the value of the memory address register from the stack pointer, because stack pointer is the temporary register, the register which contains the value of the top element of the stack, which can be pushed and popped, right. So, memory address register is going to get the value of SP, that is stack pointer. Memory buffer register, you store the value of PC. So, in this case there is a memory buffer register, here you put the value of PC, and then you say write. So, if you write, the memory PC will be saved over here. Then you make SP equal to SP minus 1, that is SP minus 1, then you again load the memory address register. So, now your memory address register will be pointing to the next element of the stack, because this one you have stored PC. Now, you decrement SP equal to SP minus 1, give the value of the memory register, and memory buffer register, now you put your program status word. So, now you will have program status word, and you keep on doing it, and then you write it, then again you decrement the PC, you keep on doing it till you want to save all the elements. So, what I am doing? I am taking the SP, writing to the memory address register, and then in the memory buffer register I am putting whatever I want to save, PC, program status word, all register values I will write in this manner, and then finally I will give PC, I will load with the address where I want to jump, because now my PC has already been saved. So, I can rewrite the PC to the jump instruction. So, in this way you will jump to the respective location. Return will happen, reverse will happen when you want to return back. So, what I want to do? Again, memory address register, this is de facto. So, this is de facto. So, whenever you want to do any kind of an operation of call, return, push and pop, returning to this function call, stack pointer will be writing to the memory address register, then you will read it. So, again you will read the value of memory buffer register to register 1, and you will keep on doing it. So, what I am doing? Memory, this is the stack pointer is now pointing to this memory location. Now, this is a memory address register, this is the stack pointer, this is the default. So, now whatever in this case is now in the memory buffer register. Now, I will first write to R1, R2, R3, R4, that is all the in this case it will be or read will be there. So, you will keep on reading the values. If you see the read operation. So, first from the memory buffer register you will read R1, R2, R3, then we will be reading the value of program status word, then we will be reading the value of program counter and so forth. You will keep on doing it from everywhere. You will do register R1, you will read, then increment the value of program SP by 1. So, now it will be your new SP, you will read R2, R3, R4 program status word, and finally you will read the value of the program counter. If you remember, I have saved the program counter, then I have saved all the program status word and the registers. While I am popping, I am reading R1, R2, R3, R4 program status word, and finally I am reading the program counter. So, when you are returning the program counter, obviously you have returned from where you have left. So, basically these two slides are showing the micro level instructions or the micro level operations required to implement a call, return, push and pop. Very simple. First you have to give the value of stack pointer to the memory address register, then either do a read or write, and you have to keep on doing it till you have fetched all the or pushed or popped all the required elements. When you are calling a function, then you have to change the value of program counter to the jump instruction, and when you are returning, you have to write the program counter from the stack, because the stack will be remembering the value of the program counter where I have to return. So, this basically completes this module as well as this unit, where we have started from what is a very basic CPU architecture, then how instructions are designed, and finally we have ended to a very complex set of instructions which are involving procedure call, return calls, and what do I say, that is your conditional jumps, etc. So, in the next module we will be trying to look into more internal details of a CPU architecture and how these basic instructions are executed in terms of hardware signals. So, before we close down, let us see one or two simple questions. So, given the organization of a CPU, how, or a nested procedure, how call and return can be incorporated? Mention the name and purpose of several of the hardware elements required to do this. So, if you are able to answer this question, it will means suffice for the objective slide, describe the concept of modular programming, discuss the basic requirements of CPU design, and also discuss in details about the return and issues of call and return instructions, because when you will be solving this problem, you will be able to justify these objectives. Second similar question can be, mention the general micro operations needed for the push and pop, return and call. So, as we have last discussed, what are the basic micro level instructions required for a proper procedure call and return. So, this actually directly satisfies the objective of synthesis design, that is explain the issues of design and call return instructions, and how internally they are designed and implemented. So, with this we come to the end of this module, as this lecture as well as module. So, in the next we will be looking at in a newer module which will be looking into more details on the hardware aspects of execution of the instructions. Thank you.